Alright, in this video I'd like to talk about average atomic mass and do an example. So we know from previous videos that each proton and neutron in an atom has a mass of about 1 atomic mass unit. And then electrons weigh so much less that we can kind of ignore them unless we're doing something really accurate in terms of the mass. And so therefore, the atomic mass of a single specific isotope of an atom in atomic mass units is approximately equal to its mass number. As an example, a chlorine-35 atom has a mass of 34.9689 AMUs, so roughly 35. However, most elements exist naturally as a mixture of at least 2 isotopes, sometimes more. And so if I'm dealing with a sample of atoms, I have an average mass in terms of the atoms of all the isotopes that are present. Now, what complicates calculating the average mass of the atoms in my sample is that not all of the isotopes exist in nature with the same percentage. Some of them are more abundant than others. And so the average atomic mass that's listed in the periodic table is the weighted average of all the isotopes that are present in the naturally occurring sample of that element. And so let's take a look at how that's actually calculated. Right, so this number that's in the entry of most periodic tables is the average atomic mass. Now, most of the time we're lazy, and when we say atomic mass, we mean this number, but what we really mean is the average atomic mass. And the formula for calculating that is shown here. And if you haven't seen this notation before, this Greek uppercase sigma is what we use when we represent sums. And so what we're going to do is we're going to sum, or we're going to add up all of the isotopes of a given element. And I represents each isotope. So we're going to go over all of the isotopes, and for each isotope, we're going to take its fractional abundance, so the percentage that it appears in nature, only written as a decimal, and then for each isotope, we'll multiply its abundance by the mass of that specific isotope. And we'll do that for each one of the isotopes, and then the sigma says, then sum them up, add them all up. Right, as an example, if I wanted to find the average atomic mass of chlorine, I would look up and see that chlorine has 2 naturally occurring isotopes. There's chlorine-35 and chlorine-37. The abundance of chlorine-35 is 75.77%, and the abundance of chlorine-37 is 24.23%. And then the mass of a chlorine-35 is given here. The mass of a chlorine-37 is given here. So what I would do to get the average atomic mass is for each isotope, so for chlorine-35, I'll take its fractional abundance. And so to get the fractional abundance, just take the percentage and divide by 100 to get the decimal. So 75.77 in decimal form is 0.7577, and multiply that by the mass of chlorine-35 isotope. And then add that, that's what the sum means, to doing the same thing for chlorine-37. So I took the abundance of chlorine-37, divided that by 100 to get a decimal, multiplied it by the mass of chlorine-37, and then add those up. And when I do that, it gives me the average atomic mass. And so one nice thing about these problems is very often you can check your work. If you don't get the average atomic mass that's on the periodic table, you probably did something wrong. Of course, I'm going to ask that you show your work on these problems, or I won't give you any credit for them. You can't just look at the periodic table and write that down without showing me any work. Right, so how this would differ from a non-weighted average, which makes this a weighted average, is if this was a non-weighted average, then for each one of these, we would have just used 0.5. We just would have used a half. Or if there had been 3, we would have used 0.33333. If there had been 4 isotopes, we'd have used 0.25. And that would have given us sort of a regular mean, a regular average, like we might normally do for averages. What makes this a weighted average is rather than using 0.5, I use the actual abundance of each isotope here. So that's what makes it a weighted average. Alright, so let's finish off with doing another example. So I'm given the same information for silicon that I was just given for chlorine, but silicon has 3 naturally occurring isotopes. And I'm given the mass of each isotope, and I'm given the abundance of each one. So what I need to do is first convert my abundances to decimals. So I'm going to divide all of those by 100. So I'm going to get 0.9223 careful with your decimals here. It's 0.0468 and 0.0309. And then what I can do for each one is multiply the mass of each isotope by its abundance. Now you could do this all together and put it in your calculator all at once, but I want to be a little bit more careful because now I'm doing mixed operations. I'm doing addition and subtraction and multiplication, and I need to be aware of my significant figures. So that's why I'm going to break it down into a couple steps. So when I multiply these out, silicon 28, 27.9769 times 0.9223, I get 25.8031. And if I do the same thing for silicon 29, I get 1.3561, and I get 0.9262. Now, the reason I wanted to break this down is because when we consider the significant figures, for this first operation, when I multiplied these two numbers, I have 6 sig figs and 4 sig figs. So in my answer, only 4 of these are significant. And so sometimes what I'll do when I have multiple steps like this, and it's good to keep more digits than we actually need. If we round at every step, that introduces more error. So it's usually best to wait to do the final rounding until the end. And so I'm going to keep more sig figs than I need. I really only have 4 sig figs, but I kept 6 to reduce my rounding errors. But what we can do is underline the last number that's significant. And in fact, I'm going to change here. Let's use a different color to do that underlining. Right, so the last significant digit is, and that number is the 0. I'll underline it in red. For the next isotope, I have 6 sig figs and 3 sig figs. So I only have 3 sig figs in my answer. So the 5 is the last number that's significant there. And then again, 6 sig figs and 3 sig figs in the next one. So the 6 is significant. But when we're doing addition and subtraction, as we are now, we don't count the number of significant figures. We look at which one has the first decimal place that's not significant. And so I have to cut it off here, because in the first two numbers, nothing past the 100th place is significant, so I can't report anything past the 100th place as being significant in my final answer. So I'll add those up without doing the rounding, and I'll get 28.0854. And now I'll do my rounding, so the 5 will have me take this to 28.09 AMUs. And if you go to the periodic table to 2 decimal places, the average atomic mass of silicon is 28.09 AMUs.